Let's move to another architecture, which is voltage regulated power architecture, or we call regulated bus architecture. Still, the uniform voltage distribution maximum power tracking control is applicable. In this architecture, we still have 3 power sources, 3 dipole converters, the same battery, the same controller, except something add into the controller to regulate the regulated bus voltage called Vout. On modes of operation, always keeping equal sourcing voltages across power source number 1, power source number 2, and power source number 3. The system bus sourcing current that sourcing by the 3-channel dipole converter I-bus and the system bus voltage V1. These two variable feedbacks signal is used by the maximum power tracking control to track the system optimum power. The controller have in addition to the previous feedback signal, we have additional feedback variable called Vout to regulate it stiff and firm like an ideal voltage source, and generate additional control signal that control the output isolated output converter to regulate the total system output voltage. This chart shows the system block diagram of the system controller for the voltage regulated power architecture or regulated bus power architecture. As you can see, the control block diagram mostly identical to the system controller diagram shown for the battery dominated power architecture, with the exception that we have output voltage regulator controller add for the to regulate the bus voltage Vout. Another subtle difference in this control architecture, we also provide an option that we can feedback the sourcing voltage variable using the maximum limit detection. This particular feedback variable is VDIS. This feedback variable is controlled and regulated corresponding to the set point voltage VSPT, which is the maximum power tracking candidate. It's the maximum power tracking voltage candidate to which the VDIS is regulated. In this particular controller, they also have some subtlety in the maximum power tracker that use only I-bus as a feedback signal. I-bus have AC ripple that proportional to the power variation. In wave, I-bus represent power signal quantity in terms of its AC variation. The maximum power tracker controller detect the control direction toward the peak power using two variables. The variation in powers, that one variable. The other variable is the variation in sourcing voltage, which is the same as the digital signal. Since the digital signal is the command that become a command AC ripple, and the system sourcing voltage either V1, V2, V3 always tracking that AC ripple. In this manner, we don't need to have the sourcing voltage as a feedback variable to the MPT controller. Instead, we use the digital signal injection that already exists in the MPT controller as the signal to process the direction toward the peak power. Make the MPT controller become simpler, easy to design, and at the same time, the signal to noise ratio is much better because the digital signal is internally generated without being corrupted by the noise generated by the switch mode converter that propagate the ripple into the sourcing voltage. This chart shows the simulation results of the voltage regulated power system. The distributed sourcing voltages V1, V2, V3 are tracked at around 32 volts DC, which is corresponding to the voltage that allow the optimum power transfer. During this mode of operation, the system regulated bus voltage Vout still solidly regulated at 28 volt DC without any observable disturbance. During the maximum power tracking mode, the system load current draw from the bus is 28 amps, which is make it exceed the total available system peak power, causing the system to go into the maximum power tracking mode, and on the sourcing voltage reflect the digital or AC ripple superimposed on its operating point. This ripple is about 20 Hz. In both modes of operation and showing their transition among these two modes between maximum power tracking mode and non-maximum power tracking mode, review the robust system without any undesirable oscillation or instability. This chart uncovers the simulation result of multiple fault tolerances. The chart showing two plots. One plot on the right is a time domain simulation, and the plot on the left is the trajectory simulation that created from the same time domain simulation. The trajectory that show on the PV curves in red color transit from point A, B, C, D, and E, showing corresponding 7 peak power points that have different peak powers due to different failures among those power sources. At point A, we have power source number 3 fail. At point B, we have power source number 2 fail. Point C, power source number 1 fail. Point D, 2 power source fails. Power source number 1 and power source number 3 are failed. And eventually, when the system restores, all power sources are able to provide their powers, then the peak power at point E is finally restored to be at 1357 watts, and the system summation of sourcing voltage is 96.9 volts, which is corresponding to about 32.3 volts per power sources. Despite of the failure of one or more power sources, the high power tracking efficiency is still able to be obtained and able to tolerate up to n-1 faults, provided that the system has n channels with n distributed power source.